Hey guys, and welcome back to another calculus video. In this video, we're going to talk all about physics. So we have discussed some things about physics in previous chapters and sections. Remember when we have a position equation, I'll call it S of t. If we take the derivative of that, then we're going to get velocity. And then if we take the derivative of velocity, we're going to get acceleration. And that happens to be the second derivative of the position vector. So it would only make sense that I should be able to go backwards. That is, if I know acceleration, I can get to velocity. And if I know velocity, I can get to the position equation. So let's derive where all of these equations come from. And we saw these back in the pre-cal series. We talked a little bit about acceleration and velocity and the relationship with position. So we know, let's say we know acceleration, and we do because we know gravity's force, and we can integrate that to get velocity. So I'm going to call that g, because on Earth gravity is a constant force and it is an acceleration. And in physics, g is equal to negative 32. That's going to be feet per second squared. And if we're in metric, is equal to negative 9.8 meters per second squared. So if I integrate that gravitational force, I'm going to get velocity. So when I integrate that, remember, this is just a number. It's either this number if I'm talking about feet per second, or it's this number if I'm talking about meters per second. So I'm integrating this with respect to time. So it's going to look like this. G times T plus C. Now, we usually know something. We usually know at the beginning of our experiment what the initial velocity is. So suppose we know that. So at time 0, then the velocity is some initial velocity. I'll call it V naught. Then we have an initial condition, and we can figure out what C is. So I'm going to plug V naught in for my V here. 0 is going in for T, and you can see that constant's going to be V naught. So now my velocity equation is GT plus V naught. And if I want to get back to position, we're going to have to integrate that. So position is going to be the integral of the velocity. I'm going to integrate GT plus V naught with respect to time. So T is the constant of integration. So I'm going to add 1 to my exponent divided by my new exponent. V naught is just a number, so I'm going to integrate with respect to T. When I integrate a number, I'm going to get that number times T. And then we're going to have plus some C value here. So there's my position equation. But we usually know something about position too. We know where we were when we first threw the object or dropped the object. So we know an initial condition, which means we can solve for C. So suppose we know at time 0 what that initial position is, and I'll just call it S naught. So let's substitute everything we know into here. So I'm going to have S naught is equal to, I'm going to write this as 1/2 G. My time is 0 because this is the initial condition. It's what's happening at time 0 in physics, plus C. So I'm going to get S naught is equal to C. So the position equation is going to be 1/2 GT squared plus V naught T plus S naught. So this is how things are going to fall on Earth, and that's if we ignore air resistance. If we know the position, so where it was dropped from, initial height, and we know how fast it was thrown. If we're throwing something, if we drop it, then the initial velocity is 0. Then we can figure out the position of any object. So that's where that equation came from back in 171, is really just based on the idea that gravity has this particular force depending on which system you're working in, whether it's the Old English system or the metric system, and then we know the relationship between velocity and acceleration and position. So now let's think about these ideas and let's apply these ideas to different problems. And some of these problems are going to change our position equation or whatnot. So we have a ball that's thrown upward from a height of 2 meters at an initial speed of 20 meters per second. So that initial height is 2 and the initial speed is 20. Acceleration resulting from gravity is negative 9.8 meters per second squared. If we ignore air resistance, we want to find the velocity and the height of the ball 2 seconds after it's thrown before it hits the ground. Well, we've really already computed this because we derived where that general equation is coming from, but just for fun, let's do it again. So we know that acceleration is going to be negative 9.8. We're going to integrate this with respect to time. If I integrate acceleration, I'm going to get the velocity equation. So that's going to give me a negative 9.8 t plus some kind of constant. So there's my velocity. We know that that initial velocity was 20, and that's going to be at time 0. So 20 is equal to my constant. So my velocity equation is equal to negative 9.8 t plus 20. And then if we integrate velocity, we're going to get acceleration. So I'm going to write that velocity equation over here just so we don't lose it. So I'm going to get my position equation. So negative 9.8 t squared over 2 plus 20t plus some constant. That's where we're going to use this information. In the beginning, that height was 2 feet. Negative 9.8. So let's look at question 2. They're giving us a position equation, and they're asking us to find velocity. Well, this is just the derivative of the position equation. So if I take that derivative, I'm going to get 12t squared minus 84t plus 120. Then they're asking us, where is the velocity equal to 0? So we're going to take this guy and we're going to set it equal to 0, and we're going to solve it for t. That's going to give me the places where that derivative of that position equation or the velocity equation is equal to 0. So if I set that guy equal to 0, I could factor out a 12 from every term, and then it becomes something that's really easy for us to factor. Factors in the t minus 5 times t minus 2. So I'm going to get two places where that is going to be equal to 0, and that's going to be at time 2 and then at time 5. And then they're asking us for an acceleration equation. The derivative of acceleration, the derivative of velocity is the acceleration. So if I take the derivative of this guy, I'll get the acceleration equation. That's what's going on with that one. Now let's look at 7. A rock is dropped off a cliff and it hits the ground with a velocity of 34.9 meters per second. We want to know, how long was the rock falling? So let's take a look at this one. A rock is dropped off a cliff. So if it's dropped off a cliff, that means that initial velocity is 0, and it's hitting the ground with a velocity of 34.2 meters per second. We want to know, how long was it falling? So we're looking for t. So we know if we integrate acceleration with respect to time, we're going to get velocity. and we know the initial velocity at time 0. So since I'm looking at meters per second, I've got to use the meters per second velocity here. Acceleration here. So that's negative 9.8. When I integrate that to get velocity, I'm going to get negative 9.8 t plus c. So remember, this is initial velocity because we know we're going to have to use that initial condition. At time 0, the velocity is 0. So my velocity is 0 at time 0. So that means c has to be equal to 0. So my velocity equation is really just negative 9.8 t. So now that I know that velocity when it hits the ground is hitting the ground, and because it's falling, that would be a negative velocity. Velocity is going to have a direction in addition to a magnitude. So that negative tells us that it's falling. If we were to throw something up in the air, then it would have a positive velocity in the beginning, and then once it starts coming down, it would have a negative velocity. So that's going to be equal to negative 9.8 t. Remember, this is going to tell us what's happening at that moment in time. So it's an instantaneous rate of change. And if I were to divide both sides by the negative 9.8, then I'm going to get 3.54. So it's going to hit the ground at 3.54 seconds. So just a side note on this problem, we could actually figure out how high that cliff is. So let's look at how we would do that. We know our velocity equation, and if we integrate velocity, we're going to get position. So that's going to be negative 4.9 t squared plus c. I'll call that S naught because we know that's going to be our initial height, and that's what we're looking for. So what is that? What is S naught? Well, S naught's going to happen when t is equal to 0. And we know at 3.54 seconds, our height is equal to 0. And that came from when we hit the ground, the velocity, and the time that we found just a second ago. So let's substitute in what we know. We know at this time the height's going to be 0, and that's going to give us enough information to solve for S naught. So we're going to have 0 equals negative 4.9 times 3.54 squared plus S naught. And if I were to solve this for S naught, I got 61.4. So my position equation would be negative 4.9 t squared plus 61.4. So there's the height of our cliff. 8 divided by 2